In this video, we are going to explore the fascinating world of LTS systems and what happens when we connect them or when they are interconnected. And, from signal processing and control systems, LTS systems play a crucial role in many engineering applications. So, in this question, we wanted to study or maybe solve this example where we have three LTS systems that are connected, that are interconnected, some of them in series, some of in the combination in parallel. So the goal is to learn how to handle such cases. So one of the things that you wanted to know is the overall system. What are the properties of the overall system, for example? Is the system still? Is the system memoryless, or is the system it's already time invariant? So is the system stable? Is the system causal? And so on. So what we wanted to do here is to find the equivalent impulse response, meaning when I have x of t, what is the equivalent impulse response and this interconnected subsystems. Okay, so we know that for LTS systems, when we have x of t and then you have, let's say, g of t or h1 of t. Okay, you see this with so not to get confused, I'm gonna use a different variable. So let's say that I call this m of t and I call this g of t, right? And so this is the output. So we have a series connection. So when we have a series connection, right, so here we have series connection, right? So the output of the first block, right, if I call it y1 of t, becomes the input of the second block, right? So and then we call that y of t. So from what we learned in the LTS system class lecture rather, so x of t convolved with m of t, right, will give me y1 of t, which is the output of system 1. And then system 1, the output of system 1, which is y1, so y1 of t convolved with g of t will give me y of t. So what is y1? Y1 is m of t, right, convolved with x of t, or x of t convolved with m of t. We know that convolution operation is commutative, so x of t convolved with m of t is the same as m of t convolved with x of t, right? So this is y of t. So, and then we know that the convolution operation associative, so I can put the x out, and then I have m of t convolved with g of t, so which is still my output. So as you can see, this, right, is the impulse response of the system connected in series. So when we have a series network, right, x of t, and then let's say we have m of t, and connect it to the series with G of t, which is the system 2 impulse response, y of t. Then this is equivalent to m of t convolved with h of t. Okay, now so when they're in parallel, so let's say that I have x of t, so let's say parallel connection. So here we have parallel connection. Okay, so in this case we have two systems. So here we have m of t, and let's say now we have g of t here. So, and then when we write the output of each, so let's say this is y1 of t, that will be y2 of t. So the output y of t is equal to y1 of t plus y2 of t. But what is y1? Is m of t convolved with x of t. So x of t convolved with m of t plus the y2, which is x of t convolved with g of t. So, and then we know that convolution is distributive over addition. So we can write it as m of t plus g of t convolved with x of t. So as you can see, when the systems are connected in parallel, that's what we have here, then the overall impulse response will be m of t, which is the overall impulse response is m of t plus g of t. Okay, so we are going to use this two properties that we just derived to solve this question. So the first question, so our first question one is to find, so let's just find the overall impulse response. H equivalent of t of the system. So the system is given by x of t, then we have h1 of t here, and here we have h, so we have h2 of t, and h3 of t that are connected in series. And this is the output y of t. So from what we said, what we did above, we know that this 2 is h2 of t convolved with h3 of t. So that means the block diagram becomes h1 of t and we have h2 of t convol with h3 of t, and this interconnection is put in parallel. So this implies that the overall impulse response, right? So if you agree with me, we could write, if I call this y1 of t and I call this y2 of t, all right, so let me use a different color. So let's say this is the output of the top block is y1 of t, and the output of the bottom one is y2 of t. So we know that y1 is x of t convol with h1 of t, and y2 is x of t convol with h2 of t, which is convol with h3 of t. Okay, so then the output y of t, which is y1 of t plus y2 of t. So we have y of t, which is x of t convol with h1 of t plus x of t convol with h2 of t, which is also convol with h3 of t. Okay, so we use the distributivity of the convolution over addition, so we can pull the x of t out, so that gives me h1 of t plus h2 of t convol with h3 of t. So as you can see, this h equivalent, right, is this. So h equivalent of t, that's that. So what the h equivalent that we're looking for on the first question is h1 t convol with h2 of t convol with h3 of t. Now we are told, so I'm gonna copy this down there. So let me copy this and paste it down here, so we have all the questions in front of us. Paste. Now, so we found the first question, which is h equivalent of t is h1 of t plus h2 of t convol with h3 of t. Now, question B, we are told that h1 of t is t u of t plus 1. So it's a ramp function that starts to -1 and like that. Okay, so it's a function of a slope 1 that is 0 before t equal to -1, and then becomes t from t equal to -1 and above. So and then we have h2 of t, which is delta of t minus 1, and h3 of t is equal to t plus 1 u t minus 2. Now, so let's find the equivalent impulse response, right? So this is the time domain version of the transfer function, of a linear time invariant system. So the H equivalent is the transfer function, right? So this is the time domain, and the frequency domain will be the transfer function. Okay, so we are going to have a series of videos, and we're going to dive into all those topics. So we have t times u of t plus delta of t minus 1. We convolve that with t plus 1 u t minus 2. Now, so let's compute the second term. So the second term, which is delta of t minus 1, convolve with, so let's take the second term, number 2. So number 2, we have delta t minus 1, that's convolve with t plus 1 and u t minus 2. Now, so I am going to call this another function, maybe p of t. Okay, so that means I have delta of t minus 1 convolve with p of t. Now, when I convolve, I do delta of t minus 1, convolve that with p of t. Let me write that up. P of t, by definition, is integral from negative infinity to plus infinity. Okay. P of t minus tau delta tau minus 1 d tau. Okay, so that's the definition of the convolution integral. So now, when you look at this, we have a product of a function and a delta function. We have to apply shifting property. So apply shifting property. All right, property, right, which states that when you have f of t times delta t minus t0, then that is equal to f of t0 delta t minus t0. So I am going to use that, okay, here. So that means this, right, becomes integral from negative infinity to plus infinity. So the integration variable here is tau. So tau minus 1 equal to 0. So tau equal to 1. That means my t0 equal to 1. So that means I will have p of t minus 1, okay, and delta of tau minus 1 d tau. So the p of t minus 1 does not depend on tau, so we can pull that outside the integral. So minus infinity to plus infinity delta tau minus 1 d tau. But we know that the delta function, right, happens at this point 1, right, and then 0 everywhere else. So when we integrate that, what do we get? The area under the delta function, which is 1. So that means delta t minus 1 convolve with p t equal to p of t minus 1. So let's write this in general. So in general, all right, when you have x of t convolved with delta t minus t0, is just x of t minus t0. All right, so we can use this result from now on, since we just derive it. Okay, so now that we know this, then delta of t, well, so we know that p of t equal to t plus 1, right there. That's where we define the p of t. So t plus 1, okay, so t plus 1 times u of t minus 2. So p of t minus 1, so everywhere that I see t on the right hand side, I place it by t minus 1. So t minus 1 plus 1 u t minus 1 minus 2. So this gives me t u of t minus 3. Right, so the overall impulse response is equivalent with t is t u of t plus 1, t plus 1 plus t u of t minus 3. So, or if you like, is t times u of t plus 1 plus u of t minus 3. So we just computed the equivalent impulse response, the overall impulse response of the system. So I can sketch it, but where I will sketch it later on. I don't want to make the video too long. So then question C, we're asked to compute and sketch the step response. So C, step response. Now, what is the step response? So we have an LTS system. So when we apply a step input, then we get a step response, the response of the system. So a step, which is u, and the response is, we call it x of t. So x of t, which is the output, by definition is the u of t, the unit step, convolved with the equivalent impulse response. So that, by definition, is the integral from negative infinity to plus infinity, u t minus tau, h equivalent of tau d tau. So I am going to compute this convolution graphically. So I'm going to do graphical convolution. Okay, so now for graphical convolution, to do graphical convolution, let's sketch H and go from there. So let's insert some space here so I can sketch H correctly. So this, right, so this is t times u of t plus 1. Okay, now t times u of t minus 3, right, is also a straight line, but that start from that starts from 3. Okay, so we have this line still. So at t equal to 3, we have 3 for this one as well. So that other line is on top of this. So then when we add the map, then at t equal to 3, we have 3 times, well, this is 3 times u of 4 plus, right, 3 times u of 0. So that's 6, right? So if I sketch this correctly, then this is 4, 5, 6, 7, 8, 9, and so on. So it's 4, 5, 6, 7, 8, 9. So we have a jump in here. All right, so at t equal to 3, it gives me 6. Okay, it gives me 6. So at t equal to 4, right, so it's 4 times 2, that's 8. All right, so at t equal to 4 is going to be 8. Okay, so it's going to be a line like this. That I've sketched it correctly. So this, right? So then this, and 9, 10. So the line should be something like that, and the function looks like this. Okay, so the slope here will be 2. The slope here is 1. So the equation of this is just t. Let's find the equation. So let's call it tau. This is tau. So this point is 3, 6. We know the slope is 2. So this is going to be 2t plus b. So let's find b. We know that I have 2 times 3 plus b, and the value there is equal to 6. So b equal to 0. Right, so the equation of that section is 2t rather. So equation of this is 2t 2 tau. The equation of this is just tau. Okay, so let's continue with so that's h equivalent of tau. Now we need u of t minus tau. So u of tau looks like this. So this is u of tau. Then u of negative tau. U of negative tau is this. U of negative tau. Then u of this is 0, so t plus 0. So that will be u of t minus tau. Okay, so I'm gonna position u of t minus tau in here. So this is u t minus tau. So case number 1, when t is less than -1, right, there's no overlap, right? So s of t, well, in that interval, h equivalent of tau is 0. right? So then u t minus tau times a equivalent of tau is equal to 0. So that means s of t will be 0 for that. So for t less than or equal to -1, x of t is 0. So we have that. Now, case 2. Okay. So when t is between -1 and 3, before we have that transition, so -1 less than or equal to t less than or equal to 3, h equivalent of tau equal to tau. So, and the u of t minus tau is 1, right? So then x of t, right? So when I sketch this scenario here, we have this. So you have this line, so then up to 3, right? And we have this function, just t here, so u of t minus tau. So the overlap is from -1 to t. So x of t will be integral from -1 to t of tau times 1 d tau. So when we integrate, we have tau square over 2 divided from -1 to t. So t square over 2 minus 1/2. So case 3. So for case 3, when t is bigger than or equal to 3, so then what do we have? We have the overlap will be for the two graphs, right? So what do we have? We have this. So we have this graph and this graph. So let's say this is 3. So let's say this this is t. This is u of t minus tau. So the overlap is oh, I did not sketch this correctly. So the other graph is like this up to -1. So the overlap is going to be this, right? So x of t, we have two sections for overlap. To go from -1 to 3, the function then is tau d tau plus integral from 3 to t. The function there is 2 tau d tau. So let's integrate. So we have tau square over 2 taken from -1 to 3 plus tau square taken from 3 to t. So this gives me 9 over 2 minus 1/2 plus t square minus 9. Okay, so this is 8 over 2, which is 4, minus 9 plus t square. So that's t square minus 5. Okay, so then for this case, for t bigger or equal to 3, x of t equal to t squared minus 5. So when I put it together, x of t is equal to 0 for t less than -1, then is t squared over 2 minus half. That is from -1 less than t less than 3. I can close that. And then is t squared minus 5 for t bigger or equal to 3. Okay, so we can sketch this function x of t. Alright, x of t. So t here, x of t here. Let's say this is 1, 2, 3, 4, 5, 6, and so on. So -1, -2, -3. So at t equal to -1, the function is equal to 0. Alright, so x of t is 0 up to here, and that becomes 0 up to here, and so it's t squared, right? It's parabola that's gonna go that way, and then when it reaches 3, so this is roughly sketch. Reach 3, then it's gonna continue as another parabola, t squared minus 9. Okay, so it's not gonna curve up. Well, it's gonna curve up, right? Then it's gonna continue going. So that's x of t. Right? Thank you. So if you want, we can plug in t equal to 4 in this equation. So that's 16 minus 5, right? That's 11. So 4, I mean, we reach 11. It doesn't matter. Okay, so that is our graph at t equal to 3. It should be equal to the value of the function here, which is 9 minus 5. It should be equal to 4. Right, so this should be equal to 4. All right, so thank you.